Hi students, Professor Nugent here. Let's talk about autocorrelation, also known as serial correlation. The correlation of a series with its own lagged values is called autocorrelation or serial correlation. The first autocovariance of yt is the covariance of yt with yt minus 1. So we're looking at a time series of values of a variable y. You have yt minus 3, yt minus 2, yt minus 1, yt, right? We're looking at the covariance between these two. The covariance between these two. The covariance between these two. Alright, the first autocorrelation of yt is the correlation between these two sets of observations. So recall that correlation is the covariance between the two observations divided by the square root of the variance of yt times the variance of yt minus 1, and that gives us the first autocorrelation. These are population correlations that describe the population joint distribution of yt and yt minus 1, and we're going to see later in the chapter that it's going to be very important that we are able to assume that we can generalize this idea of autocorrelation or serial correlation on autocovariance to the jth lag. So the jth autocovariance of a series yt is the covariance between yt and its jth lag, yt minus j. And the jth autocorrelation coefficient is the correlation between yt and yt minus j. So let's write this down in terms of equations. The jth autocovariance, that's the covariance between an observation yt and yt minus j, where j might be, so if j is 4, this is t minus 4, so this is the covariance between an observation and an observation that occurred 4 periods prior. The jth autocorrelation is rho j, and that correlation is the covariance divided by the square of the variances. The jth autocorrelation coefficient is sometimes called the jth serial correlation coefficient. And what might be an example of this? Why do we care about this? Well, we might be thinking about if there is seasonality, then we might want to look at the fourth autocorrelation coefficient to see how strongly correlated are sales during the last quarter of the year of 2017 or the last quarter of any year correlated with the last quarter of the next year. As usual, we're going to estimate the population parameters using sample statistics. So the jth sample autocorrelation is an estimate of the jth population autocorrelation. So we have some hats here to denote that we are estimating the population parameter using sample statistics. We should have some hats here. These things are hats. So the jth population autocorrelation is estimated as the variance, as the ratio between the covariance of yt and yt minus j divided by the variance of yt. And recall that we are assuming that the variance of yt is equal to the variance of yt minus 1, which is why the denominator has simplified. So this variance of yt equals the variance of yt minus j, because we are, as you will later see in this presentation throughout the chapter, that we want to be able to assume stationarity, so that variance is constant and the distribution is constant over the sample. So the variance does not depend on time. These two variances are the same, which means that this denominator simplifies to variance of yt. We estimate the covariance of yt with t minus j as 1 over t times the sum from t equals j plus 1 to the t times yt minus the average of the observations j plus 1 through t times yt minus j minus the average of observations 1 through t minus j, where again y bar, j plus 1 through t, this is the sample average of yt computed over the observations t equals j plus 1 through t. So do note, the summation is over t equals j plus 1 through t. Why is this? So let's think about if j equals 1. Then in our observations, so we have observation 1, observation 2, observation 3, observation 4. The summation starts with t equals 1 plus 1, so the summation starts here with 2, so that we have a observation that is allowed to be a lag. So yt starts with 2, so that we have a yt minus 1. Okay, let's look at a different scenario. What if j were equal to 4? So you have observation 1, 2, 3, 4, 5, 6. Right? So we want a value to plug in for yt, we want a value to plug in for yt minus j. And the summation is computed over observations t equals j plus 1. So if j equals 4, then we start at 1, 2, 3, 4, 5. So 5 is where yt will start. Because then minus 1, minus 2, minus 3, minus 4, this 1 is where we will have our first lag. So we need to move yt ahead by a sufficiently high number of observations so that we can have a lag within the domain of y. Also note that the divisor is t and not t minus j, which is the conventional definition used for time series data. So we've been talking a lot about the equations and how, for example, quarterly sales at the end of the year might be correlated because they tend to be higher at the end of the year, or non-farm payroll, monthly non-farm payroll might be correlated from one month to the next, because if it's high one month, it's likely to be high the next month. We can see here, looking at real gross domestic product, the percentage change, that The first four autocorrelations are 0.33, 0.26, 0.1, and 0.11. So this is telling us, and this is in terms of the quarterly percentage change, that the correlation between the percentage change this quarter and the percentage change that last quarter is 0.33. The correlation between the percentage change this quarter and the percentage change 2 quarters ago is 0.26. The correlation between this quarter and the quarter 3 quarters ago is 0.1. The correlation between this quarter and 4 quarters ago is 0.11. So you have 4 positive correlations in a graph that shows some significant, I would say, volatility in the percentage change, and still you have this persistence in the growth rate. You're able to predict what the growth rate will be this quarter based on what the quarterly percentage change in domestic product will be this quarter based on the quarterly percentage change last quarter. Let's think about other economic time series. Do these series look serially correlated? Can you predict YT minus YT plus 1 based on the value of YT? Or can you predict the value of YT using the value of YT minus 1? And observe that with the unemployment rate and with the dollar to British pound exchange rate, you absolutely do have persistence. There is much less volatility than you have with the quarterly percentage change in gross domestic product. There is cyclicality in the unemployment rate as with the growth rate, but you do have persistence, and you have a lot of persistence in the exchange rate. Let's look at, you guess, one more example. Think about the log of Japan Index of Industrial Production. There is quite a bit of persistence. There's persistence here as well, but as we're going to see later in the chapter, that the persistence takes a different form over different parts of the time series. But you are able to predict the value of YT based on the value of YT minus 1 for the logarithm of Japan Index of Industrial Production. And what about the percentage change in daily value of Wilshire 5000 Total Market Index? No way. Folks, this thing is all over the place. I don't know how you're going to predict the percentage change in the market tomorrow based on the percentage change in the market today. That is a very, very difficult thing to do, and based on the efficient capital markets hypothesis, if it holds true, capital markets, I can spell capital. If this holds true, then you cannot predict the percent change tomorrow based on the percent change today. So that concludes our introduction to time series and autocorrelations and serial correlations. Stay tuned to the next video for a discussion on forecasting, stationarity, and the mean squared forecast error.